Let's consider a physical object, a complex system made of constituents interacting with a probability either between themselves or with the vacuum of spacetime. As in quantum mechanics, when the constituents of the system interact with the vacuum, it can happen across different ranges and locations depending on the nature of the interaction itself and the probability that it could unfold under initial conditions. All of this is from the perspective of the object. Now, from the referential of the universe, every interaction with the system that can occur with a probability will occur. If more than one interaction has a probability to unfold, math tells us they all do. So, the universe can mathematically perceive all the system possible locations at the position where the system interacted with it. From its point of view, the universe sees the system at each location it interacts with a probability. Yet, when a measure is made, we see the system in a fixed state and location, as opposed to a spread out distribution at once. All these states are collapsed into a single one, summing them. If all n possible interaction could happen per tick for an observer's clock, then the bigger the ratio of n per tick, the slower the system will seem to evolve for the referential of the observer. Let's consider now the evolution in time of a complex system made of constituents interacting with a probability. The system keeps the same position x between time y and y plus 1 from our referential. Between y and y plus 1, if the system was to have a probability of an interaction to happen, then the mathematics behind quantum mechanics tells us they will happen and the universe will record them as occurring. Yet were we to look, we would see from our referential a constant and changing position x. For the universe, every position is a combination of probable location and states. When we measure the system from our reference, it occupies a defined space field, but at the same time, the universe measures the same system with a different field, summing all possibilities. Our perceived field beta is the same as the universe's field of possibilities alpha. In short, what we perceive as a system space field is a reduced form of what the universe's field looks like when we both perceive the same object at the same instant. Superposed at the same time, we can grasp better how what we observe is the reduced form of all the possibilities at once, a reduction depending on our interaction with the system, the rate, the distance, and much more. Following the sound reduction reasoning, the system's full array of possible location and states as perceived by the universe are being constantly measured in a reduced form by an observer in the system's referential. Were we, for example, orbiting a highly interacting and complex system with a source of light in the background, this reduction would be more easy to grasp. In all three cases, we have the system measured location in black, as perceived by an observer, and all the object possible location as perceived by the universe in blue. Each case is different depending if the light is in the background of the system at all, or the reduced field, or the object's background as perceived by an observer. For the sake of simplicity, let's consider that the universe perceives the object at any moment as being 99.9996% in the middle region X, same place where the observer sees it reduced, and the rest 0.00001% at region A to its left, B above it, same percentage, C to its right, same percentage, and finally D below it, same percentage, 0.00001%. All of X, A, B, C, and D represent 100% of the possible locations. In this case, in case 1, we have no source of light in the background for our system, and the reduced form is simply the observed object. Now, in the second case, same distribution as in above for the X, A, B, C, D regions, but in case 2, there is a source of light in the background, let's say around the probabilities for the object's positions A and B. So we will end up with the light being 99.999996% of top left of the region X and 0.00001% above A, and as you guessed, same percentage left of B, and same percentage top far right of C, and finally it would have the same percentage 0.00001% to be top left of D. The reduced form combining all these states at once would give us a smeared light effect. As you started to grasp, in the third case, if light was 99.999996% behind X, it would be hidden in that case. But for all the rest, it would be observed all around. This would give us a reduced form for an observer where light is smeared all around the object at once in a lens-like form. This reduced form of all possible states at once gives us the illusion of curvature.